Um, Good morning, one and all. Thanks so much for joining us. I'm Nitin. I'm from Netflix, and this is my colleague Kedar. We work in the personalization infrastructure team. The team's charter is to make sure that we make machine learning easier for our research engineers. So let's dive right in as to how we build a fact store for Netflix recommendations. At a high level, we'll go over how recommendations at Netflix works, what exactly is the problem we are trying to solve in terms of experimentation, why do we, the standard battle between fact logging versus feature logging, and how we actually ended up implementing a fact store and what are the challenges along the way. So at a high level, recommendations at Netflix almost, it's kind of public knowledge right now that every single homepage for every single member of us is personalized. Given that we are launching titles almost every single day, and we're a global company, and the member base is also constantly growing, it's imminent that we find the right title for you, for the right members at the right time. The risk of not doing that, people might abandon the service because they might lose interest as the most recent content doesn't surface or something that is not relevant to them shows up. The challenge for us is to be doing this at the scale, especially given that we are global and we are launched in multiple countries. So doing recommendations at scale is what makes some of the challenges that we're going to talk much more interesting. To give you a very high level of the scale of Netflix, we have about 125 million plus active members. We're launched in over 190 countries. We have around 450 billion plus unique events that are flowing in, and they are spread over around 700 plus Kafka topics, which we use for streaming. So before we jump into the solution of why we built that, a kind of a peek into what experimentation cycle looks like. It's a traditional machine learning cycle that we talk about. So we have the offline world and the online system. In the offline world, typically someone comes up with a new experiment to run, saying that, hey, we have a production experience. How about if we add this idea, would it be better than the production experience? So they come up with a design experiment and a hypothesis and say, okay, can we collect data corresponding to this? So they define newer features. They collect the data required for the new features and then do typical feature engineering, which is offline feature generation. And with the newer features, then they train the model and do some kind of model validation and metrics, and then actually test the model against the data to see if the offline newer idea that we had is actually better than the current online or an A/B test experiment. If that is the case, then we actually deploy that and promote it to an online A/B test to see if that is really what happens in the online world. So what we are trying to do at a higher level is to promote more offline experimentation in a faster way so that we don't have to pay the cost of making everything an online A/B test before getting enough data on the offline world. And as most of you might have imagined, offline world is completely driven by Spark, which is a good segue into the next slide. So we have the offline experiment and the online view. In the offline world, all the features that we care about for feature generation and feature engineering are stored in S3. They're actually primarily stored in Hive, which is backed in S3. So S3 is kind of an abstraction in this slide, if you will. And then we have offline feature generation libraries and frameworks that have been homegrown at Netflix, which are heavily reliant on Spark. And then we also do model training. A different kind of models are being trained, again, on Spark. In the online world, things are slightly more different. So most of online services are providing the facts that are required for the feature generation themselves. And these come from a variety of microservices. There are tons of microservices within Netflix, as you can imagine. And once these facts are getting through the online feature generators, they are then converted into feature encoders through common feature encoders. And then they are being passed on to online scoring services, which then serve the recommendation for you based on if it's an A/B test or a production experience and everything like that. And in the offline world, after the model has been trained, and if we feel that the offline model is better than the current production model, then we actually deploy the model, in which case the online scoring, as you can see, will get updated and pick up the new model. The key takeaway from this slide is the online scoring and feature generation and the offline feature generations use the same feature encoders, which is a key takeaway for us because we use the exact same classes, exact same libraries, and the same data format. So in which case, the offline and the online world can have same code reusability, and it's much easier to use the same set of or the same paradigm in the offline world for training as well. Now that I kind of briefly touched upon a fact, so just to elaborate on that, what exactly is a fact? A fact is kind of an input to a feature. It's input to a feature encoder if you indirectly. So a few examples of facts are what exactly is a viewing history of a member, what did the member view, what is in his mylist, and did he give any thumbs up or thumbs down ratings for a few of the titles. So these are examples of facts which are basically source of truth. For the purpose of this talk, I would say there are two properties of the facts that we are very interested in. The first one is a historical version of a fact. We want to be able to understand what a value of a fact at any given point in the past was. And that fact needs to be temporally accurate, because as you keep watching more stuff and do more activities in the website, or the Netflix app, your facts are growing over time. So we want to make sure that we are capturing the facts that are used for recommendations. To drill in a little bit as to why historical version of a fact is important. So let's say you're actually browsing the Netflix app. Sometimes you scroll down or you actually search to find the right title for you. Ideally, we don't want you to do that. We should be serving the right recommendation for you, so just go into the Netflix homepage and start playing. So how do we get you to do that? So in order to do that, we need to be able to generate a recommendation that was closer to what you played, but in the offline world. So if we were to do that, we need to understand what the kind of the state of the world was for every single fact at a given point in time, so that we'll be able to leverage that to generate a recommendation that is much closer to what you actually played, and then promote that to an A/B test so that your recommendations are getting better. So in order to achieve that, there are a few different ways of achieving the same thing what I mentioned. The first is, so we have online scorers. So when the online scorers actually do the scoring and have your features ready, you can actually log those features to S3 or Hive, and then you can leverage them for your offline training mechanism. This will work for the most part. The only challenge is that if you want to have new features and you want to experiment with them, then you need to actually push them to the online scoring service, wait for it to go live, have enough data before you can start analyzing that. It kind of hampers experimentation cycle. Another way to do that is fact logging, which is instead of logging the features, actually log the facts. So the facts that are coming from multiple microservices that are used for the features, if you log them, then in the offline world, if a data scientist comes up and says, hey, you know what, I want to experiment a new feature consisting of a few different facts. Since we've already logged the facts in the past, we can go back in time and understand, kind of like a time travel, if you will, to go back in time and understand what the value of the new feature that you're trying to add would have been at a certain point in time in the past. So this promotes faster experimentation instead of waiting for the whole deployment cycle, and enables much more offline analysis to be easier. So what did we do? We implemented the first version of the architecture. Let's call it the pull architecture to be simple. So we have a Spark-based pipeline which ran every day. It queried some of the key facts from key microservices, and then it stored it as Parquet compressed files in S3, mainly because some of the algorithmic engineers prefer it to be in a columnar format for faster experimentation. And also, not every single member's data need to be captured. Some of them would be interested only in a few members who are in the A/B test or some kind of stratification. So we also stratify the set of members for whom we wanted to collect the data. And also, we provided a query API where people were able to query this data using RDDs or data frames. But there are a few drawbacks with this approach. One was it lacked temporal accuracy, which was one of the key properties that I mentioned in one of the previous slides. The challenge here is, for example, your recommendation or your online scoring would have been done sometime, let's say, in the evening, but the Spark job would have been run for you sometime in the morning. So even though this architecture helped us to be from ground zero to somewhere, it wasn't exactly giving you the temporal accuracy which was required to bridge the gap between the online and the offline world. The second is, as you can imagine, since it's a Spark job, hitting the microservices, we had to make sure that they are scaled up, and we are not affecting any online query, the request path. And third is, the Spark was actually only querying a subset of the facts, the most important facts, if you will, but at the same time, it was missing experimentation-specific facts. For example, I might want to log some A/B test specific information, which couldn't be done in this model because it's quite frankly not possible. So what can we do? So we just flipped the whole thing around. We made it a push architecture. So in this case, what happens is the online compute services themselves decide to log what they want to log and how much they want to log. So an online compute system would now inject one of our libraries, like fact logging libraries, and it would say, hey, I want to log for XYZ users. I want to log some of the experimentation facts and some of the key facts that are recorded from the microservices. And as I mentioned, the stratification is now up to the compute service themselves. They can decide to log it for all the members, or they could log it for some members based on, let's say, I want only a hash function, and everything that satisfies that hash function need to be logged. So the compute services are completely in the driver's seat when it comes to this methodology. And more importantly, it satisfies the second property which we're interested in, which is temporal accuracy, because now it's logged exactly at the time when a recommendation is being served to you based on the online compute service. So the other few components are, you have a fact transformer, which is in Spark, and then the actual data store, which is Hive backed by S3. And then we provide a query API, kind of like a fact fetcher, if you will, to query this data and then return it in the same format required by the ML workflows like feature generation and model training. Zooming in a little bit, so FactLogger is a Java library which is being ingested by our compute services. It allows you to log different sets of facts, like user facts, video-related facts, any computation-specific facts. And so basically what it does is it also provides a way for you to do stratification. So in this case, it would be like, oh, log X% of the users that you care about, or give me a hash function and I will tell you whether to log this guy or not. Some examples that I could think of right now. And then once that is done, we actually serialize all these fact data and send it through Kafka. So some of these facts are used across the place where backward compatibility is very important. So we use protobufs for that to make sure that they are backward compatible. And then they actually go through the Kafka pipe and then land up in the base fact tables. And as you can imagine, this became widely popular and the adoption increased quite a bit. So the challenge was people started using it left and right, and we even got notified by our Kafka folks that we were using way too much data. So the most obvious thing to do for us is to add compression. So we added like GZIP on LZ for compression, and we reduced the data to about 70%. But still, there are a few properties that were fundamentally different about the push architecture that could leverage, make us leverage a completely better data storage or better data storage mechanism. And to talk over some of that, here is Kedar.
Right. Thanks, Nitin. Hello, everybody. So let's go through the journey of the architecture, some of the challenges that we faced. As Nitin mentioned, we started logging these facts. Now think of these compute services as different microservices or applications within Netflix. And there's many of these applications logging these facts. The compression helped us quite a bit. But to make sure that we didn't get kicked in the gut once again, we wanted to make sure to try and scale further. What else could we do? So one of the things we did is we broke up these facts that were being logged by these applications into two logical sets, so to say. One is a core set of facts that are common across to all the applications, and we said we'll treat them in we'll give them first-class treatment. And the other facts were more related to the application or domain-specific facts. What did this help us do? This helped us do deduplication. What that means is, imagine there's a corpus of members that multiple applications are computing the recommendations for. These core set of facts might not change across members. It's the same set of members that are being computed for by different applications. So we were able to get a large amount of deduplication for some of the facts. And what that meant is we were able to conditionally push those facts down our data pipeline. A consideration here is, now there are two applications. What if an application sent a fact and just within seconds another application sent the same fact, and we were able to ascertain that the value was the same for those set of core facts? Should we still send the value irrespective of whether it's made it to the base tables or not, to the data at rest? And that's the consideration of how aggressive we are when we do deduplication. Now that was what helped us there was our data pipeline. Our data pipeline is pretty solid, and we went the aggressive route. So in case of, once we saw a fact, we said, doesn't matter if another one sees it a second later, we are still going to not send the fact. And what we do is, for these set of core facts, you see a value once, you send the value, you see it again, we just send a pointer. Out on that image, I have something called EVCache. EVCache is an open source library from Netflix. It's actually a library that's cloud native to Memcached. So it's a distributed cache in the cloud, and it's a library that talks to our discovery services and gives you access to a distributed cache. So we used EVCache here to store the fact whether a particular fact was deduplicated or not. All right, so now we get down, the data goes all the way down, and we have our ETL. By separating these facts into two logical pieces, one which is repeated or not, it led to a normalized structure. So in a sense, we have a pointer to our data sometimes, and sometimes we just have the value. So the job of this Spark job here, which is the fact transformer, is to peek into the facts. The applications are just sending us blobs of data. So this fact transformer actually peeks into this, pulls out the base facts, and normalizes the storage. I also mentioned that there's multiple applications logging this data. So an SLA from a read perspective, now once the data is into the base, into the fact store, which is S3, there are different SLAs for different applications. Some applications are fine reading it a day later, some applications are fine reading it 10 to 12 hours later, but some need it a couple of hours later, right? And so this fact transformer needs to be scalable enough to finish the ETL in time for all the apps. We'll delve a little bit into what I meant by the normalized storage of facts. So let's look at this table here. There's, let's say there's 3 of these core facts that I talked about, or the first class facts. Let's say you have the view history, mylist, and there's multiple rows here. And what we achieved for the second row, which is highlighted, we got lucky and we said, hey, you know what? For that row, we had seen all those facts, so we never really needed to send any value across our Kafka pipeline, so we got lucky there. However, when we start looking at the read API, the way this needs to get resolved for that member is for each of those values, we have to go look it up in different tables. And these tables here are really Hive partitions backed by S3. And as you can imagine, each of those could point to a different point in time. Like some fact, you might have to look back a day, another one, you might have to look back weeks. And multiply that 1,000,000 times or millions of times for our training sets. And what we got was our clients telling us that the performance was not acceptable. And the reason for this was the life cycle of different facts is different. Take, for example, a member's registration country. That rarely changes, right? Whereas a person's viewing history might change from time to time. So for some of these facts, what we realized is we were going back months to fetch the data, and that was just leading to hundreds of terabytes of shuffle data and killing us in performance. The fix there was simple. What we said is we'll have, if we see a fact again after a certain number of days, we'll just push the value no matter what. Now we had a read API, and we realized that there are 2 primary use cases that lent themselves to the point query lookup. Now, what does that mean? So think of it, you're trying out a new idea, and you just want to work on a small data set. You know, you've got hundreds of millions of records in there, but you want to play around with 20 records, 100 records, or 1,000 records first. Another one is the production jobs that we have that use a sample set of the data that's logged. And that's between 5 to 10% of the data that gets logged. And so when you're talking of gobs and gobs of data, it's really lending itself to a point query. So even though we were able to get our read using Spark in the acceptable time frame, for this use case, we said, why not also write the data to a cache? And the cool part about this one is that think of this as a cache connector. So just like you have a Cassandra connector, At this point, what we have is a read and write to EV cache, which is again an open source library that we have. And we were able to do read and write to a distributed cache from within Spark. This helped us reduce our latency for these certain jobs from multiple hours to tens of minutes. And that was a huge win. The next 2 slides will look at some design considerations that we had from a performance perspective. Think of what we had to think of was how do we scale this out for the future. So when we were designing our partitioning scheme, we had to account for the noisy neighbor. Not all applications log the same amount of data, not all data is sized the same. So how do we design it in such a way that if we wanted to switch over tomorrow to either the streaming use case or we wanted to run it only for certain applications or a group of applications, how are we able to scale this? So we had to think about how to partition it efficiently. Nitin mentioned that one of the crucial use cases is we have shared feature encoders in the online inferencing as well as in the offline case. And our online inferencing is all happening using POJOs, Java POJOs. And so it's nice for us to send it all as protobufs, where we have the schema maintained for us. And it also helps us that once we store it in EV cache, everything is in protobuf. So you just get it and you serve it. However, for the exploratory use cases, which is like when some algorithmic engineers want to try out their ideas, they want to use all the goodness of Spark SQL. So they want to use data sets, they want to use data frames, they want to be able to do filtering, do use predicate pushdown. And for that, you really want to have a nested Parquet kind of a solution or a storage format. Think of it if we didn't have it. So imagine you had hundreds of millions of rows and they wanted to filter it by a certain criteria, like maybe a country. If we really wanted to, if we didn't have the optimization that predicate pushdown offers us, we'd be slamming the network from EV cache or the cache across our network and then deserializing all the objects and then doing a filter. So it's an interesting challenge as to how do you serve both the use cases, where you have a very strong use case for exploratory and another use case that you just want to do your production pipelines. While we talked about the gain from multiple hours to tens of minutes from the cache, we have to realize that this is an expensive solution. Our cache is SSD backed. And so where we have a negotiation there is with our clients is there's a look back limit. We have this notion of a fast lane or a hot cache and a slow cache. And it's only up to that period of time that data is stored within the cache. Beyond that, you pay the slow tax lane. Some of the things that helped us from a performance perspective, a lot of the shuffles that I mentioned about when we were doing tens or the high tens of terabytes of shuffling data, we used Bloom filters that Spark offers, and that did help us. So if you haven't played around with it, please do. You still have to do some manual tuning around the false positive rate, where you land at a happy spot. That helped us. I mentioned we were able to write a connector to EV cache. The cool thing about EV cache is it internally uses Spectator, which is another EV cache open source tool. And what we were able to get as a result of that is Spectator acts as a sink for Spark metrics, and it actually allows us to emit all those metrics out to our metric system. So we were able to get all these things like cache hit rates, cache miss rates. We were able to see the network throughput and everything. Both of them are open source, and if there's interest, we can also open source a small example of how you would actually use a connector for EV cache out in, using all the open source code with Spark. Okay, so the blue box is where we sit. We are the read API. Now the way our API, which is it's a Spark job, is used is it's not used directly. We have a machine learning library, which is again in Spark, which sits on top of our read API. And then finally, we have an application layer, which is also a Spark job that uses that. And so it's 2 layers deep that our read API gets used. And hence, the Spark tuning is really not in our hands. We are at the mercy of the Spark tuning parameters that are passed down. So when we did the cache connector initially, the EV cache connector, we did something similar to what we have in the Cassandra connectors. We did up map partitions. And we said, hey, OK, you have a singleton, you have map partitions, and we're able to get good performance. However, again, our clients were not happy. The reason being is what we were doing is we were just adding columns to the data frame. And once you have map partitions, for Spark, that's opaque because it doesn't know how you've mutated the data frame. And as a result, performance fell down. And so we said, hey, OK, let's get back and do it as a UDF. And we implemented that as a UDF. So this was essentially going from eager evaluation to lazy evaluation. And we thought the performance would be nice or the similar. But turned out we were X times slower than what it was in map partitions. Turns out those are the 3 Spark Jira issues that have the details. There is this notion of marking an UDF as non-deterministic. If you don't mark it that way, Spark, for its optimization, can re-execute the UDF multiple times. And so we stumbled over that. It's just a learning to share out here. The trick is to mark it as non-UDF. Non-deterministic. Future work. I mentioned the challenge we have with living in the best of both worlds, where you can use exploratory nested Parquet storage as well as POJOs. We are trying some stuff with structured storage, so we have multiple storage patterns. The challenge we have is schema evolution. As the fact schema changes, having Hive go a nested Parquet when schema changes is it doesn't quite work. Iceberg is open source initiative within Netflix. Again, it's in its beta form, which is going to help us get over that hurdle. Again, it's in beta form itself in Netflix, but we are working with that Iceberg, and hopefully we can do this well. In the future, we most probably might go to streaming versus batch for a fact transformer. It might be a hybrid. That's because there are more and more apps wanting to use us, and some of them, for more real-time kind of algorithms, want hourly latencies. And so we'll be able to have multiple lanes and be able to scale each app independently. Finally, the first thing that I talked about was the deduplication that we did. It comes at a cost. It's always whether you want to have storage benefit or runtime benefit. The deduplication, as I said, results in us having a lot of runtime costs trying to go look back for the pointers. So it's a decision where how much do you pay for what, and not all facts are alike, and we might end up saying, hey, we'll just store some facts anyway. Any tips that you might have, any things that you've been there, done that, we are happy to listen to you, and any questions that you may have, Nitin and I are here or outside. No. Thank you.
Thank you. Give a warm welcome to Nitin. We've only got 1 minute, so if you have a question, make it quick. All right, thanks a lot.